Sip, tea,
Yes.
sip, 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 oh, tea, tea, sip, sip, sabun,
Bentar, bentar.
sip, 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 audio,
Yes. You want to present your slide by yourself or by
By myself, I think.
Okay.
Yes.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, respected guests, and respected faculty members, and dear students, both on-site and online. My name is Andriana Kusumapaturi, and I'm honored to be your host for today's guest lecture event, organized by the Department of Chemistry, Faculty of Mathematics and Natural Sciences, Universitas Jember. So today, we have a very special session with an honored guest speaker, Professor Krishna Persaud, from the University of Manchester, England. Professor Persaud will be sharing his expertise on current trend in sensor research and development. This is a topic that holds a great relevance in today's rapidly advancing world of technology and science. Also, we would like to thank everyone here today for taking the time to join us, whether you are here at lecture room 1 or attending online in Zoom. Okay, now without further ado, let us proceed with the event agenda. The first agenda will be opening from the host. The second one is singing Indonesian national anthem and hymn of Universitas Jember. The third one, opening remarks by the Vice Dean 1 of Faculty of Mathematics and Natural Science, Universitas Jember. The fourth one, documentation or group photo. The fifth one is our main session, our guest lecturer. And the last one is closing. Okay, to officially begin, let's start our event today by reading Bismillahirrahmanirrahim. May this session bring us new insight and inspiration. Okay, next, for the second agenda, let us show our respect by singing the Indonesian national anthem, Indonesia Raya, followed by the hymn of Universitas Jember. We invite the audience here to stand.
Sorry. That's right.
Is this question in your answer? Our third agenda, we would like to invite Dr. Anandamani Sulistyawati and Assistant PhD, the first one of the Faculty of Mathematics and Natural Science, Universitas Jember, to deliver the opening remarks and officially open today's event. To Mrs. Hari Sulistyawati, time is yours.
Thank you. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Salam Om Swastiastu. Namo Buddhaya. Salam kebajikan. It's my great pleasure to welcome you all today. Get lecture hosted by chemistry department of MIPA faculty. I'm honored to see so many bright and curious minds gathered here, eager to learn and engage with new perspectives. At MIPA faculty, we always strive to foster an environment where intellectual growth, critical thinking, even like this, is a vital part of our mission. This provides the opportunity for our students, faculty, and large community to connect with experts fresh insights from diverse fields. Today, we have the privilege of hearing from Prof. Krishna Persaud, who is the chemical sensing or chemical reception. Progress has made significant contribution to the work of chemical reception. I tracked down his CV. He also got many medals, award, also certificate since 1995. And he published more than 100 publications in his field. And now today, we are fortunate to benefit from their wisdom and knowledge of experience. The theme of today's lecture is talent in sensor research and development is one that especially relevant to specific competence develops this department. I encourage all of you to take full advantage of this opportunity, not just to listen, but to ask questions, challenge assumptions, and expand your understanding. This is a chance to learn from one of the best in the field, and I hope that today's lecture will inspire new ideas, provoke thoughtful discussion. Before we begin, I would like to express my heartfelt to Prof. Krishna for taking the time to share his expertise with us today. And we deeply appreciate your commitment to education and knowledge sharing. Without further ado, let us welcome to Professor Krishna. So that will be started. Thank you.
Thank you very much. It's a pleasure to be here today. It's a pleasure to be here with you today. Okay.
Because next is maybe
Yeah.
Thank you, Mr. Wasi, for the important remark and for also coming to today's questions. Okay, before we proceed to our next session, we would like to capture this moment with a group photo. Maybe Hari, Mr. Jurusan, and Mr. Krishna will take picture together, and the audience is in our agenda. Come forward.
So officially, okay.
Have to the screen. Okay.
Yeah. Okay. 1, 2, 1, 2, 3. Okay. Okay, that's what. 1, 2. Okay.
Okay. Thank you.
After that, everybody stand up.
Everybody, please stand up. We will do
Because
last
they will take a picture from me. So they
Okay. 3, 2, 1. Okay. Different pose. 1, 2, 3. Last one. 1, 2. Okay.
Ini kan cuma jalan sendiri.
Ya.
Ya siapa?
Oh, so the design and computer is still monitor.
Okay.
That's Japanese.
Fine.
Thank you so much for your cooperation. We now move on to the main session of today's lecture. But before that, to lead this session, we would like to invite our moderator first, Mr. Jurusan PhD, to introduce our guest speaker at today's session. Mr. Jurusan, the time is yours.
Thank you very much. Thank you very much. I thought that we just go faster to our agenda because I've been already mentioned about the curriculum vitae, but there is still some information. Miss Professor Krishna graduated from University of Newcastle upon Tyne in the area of biochemistry. So their work in this area consistently. Until now, he worked in olfactory system. And then Right now, he also have some many medal and also competition. So I don't want to mention further about the background. And here now, Professor Krishna would like to deliver the subject, the current trend in sensor research and development. And let me give some information that if you want to ask after the presentation, just raise your hand. Thanks. That's your time.
Thank you very much. It's a real pleasure to be with you today. I'm going to talk about current trends in sensor research, focusing mainly on activities at the University of Manchester. So without further ado, this is the North Campus of the University of Manchester. And this one, when you recognize this? Yeah. So this is Piccadilly Station here. This is the Maths and Social Science Tower where your director did his PhD. This is the Faraday Building where Dr. Sawyer did his PhD. In fact, this North Campus has now changed completely from what it used to be. So this building here was originally the chemical engineering building where I worked after this building, the Faraday Building. And this is a city center university. And the North Campus was used to be known as the UMIST campus, the University of Manchester Institute of Science and Technology. Now it is merged with the Victoria University of Manchester, and this picture shows this is the main building at UMIST, which was actually built in 1854, a Victorian building. And this is the main building of the Victoria University of Manchester, which is a little bit south of the North Campus where we are. So since these two universities were merged, many things changed, and we have a lot of new buildings that were constructed in the last 2 years. And now, this is now the engineering building where we're actually located. So this is in Upper Brook Street, maybe you remember Upper Brook Street. And this is a huge building, about 200 meters long, and about six floors. And houses chemical engineering, electrical engineering, mechanical engineering, and so on. So quite a lot of activities in this part of the building. Now, within the university, we have many groupings that are akin to this one. So in the university itself, we have many groups that are working on different types of sensors. So we have top, you can see the Photon Science Institute. We have the National Graphene Institute. We have the Organic Materials Innovation Center. We have the Manchester Institute of Biotechnology. We have a virtual system. And we have what's called eAgri, which is an agricultural research center for sensors. So each of these groupings have people who work in various institutes, and they also have collaborations across institutes, because working with sensors is very multidisciplinary. So I'm located with in this Organic Materials Innovation Center, and my colleagues are Professor Michael Turner, who works with conducting polymers, Steve Yates, that's myself, and Paul Less, who is a mixture of electronics and chemistry. And then we collaborate, for example, with the Institute of Biotechnology, we have people who work with biosensors, and we have crossovers with people working in healthcare, in agriculture, in optical sensors, and so on. And of course, Manchester is very important for 2D materials. Graphene was really born at the University of Manchester, and Andrew Kane and Waslaw, they got the Nobel Prize for the discovery of the functionality of graphene. So this is a kind of a picture of the organization of sensor research. So what I thought I'd do is really just give you a quick overview of some of the activities. It's impossible to cover everything, but one important thing that overlaps very much, I think, with your interest here is in the e-agri concept, where you have electronics and agriculture coming together. And so it really combines electronics and IT community with agronomy and food science, so that you can actually engineer new systems that are dedicated, for example, to reducing waste in agriculture, increasing yields in crops, improving nutritional benefits of various types of crops. And we have a group that's headed by a man called Bruce Green, who is very important in this part of the area. So what they're involved in is, for example, telemetry and remote sensing, looking at spatial and non-spatial imaging, analysis, stream analysis, looking at inline monitoring of processes, real-time decision-making, making interventions just in time. For example, if you have a disease in a crop, to be able to find it quickly and focus where to treat a field, for example. A big aspect is actually data processing. So big data, because you can handle a lot of data if you're doing remote analysis of fields and plantations and so on. So you're looking at geographically spread data. You're looking at integration of data. You're looking at for example, looking at provenance of origin crops and livestock. And then another important aspect is exploitation. So combining knowledge, exploiting knowledge, and providing opportunities for business development in this area. So all of these are kind of things that we capitalize at the University of Manchester. So just to give you a quick example of what they work on are things like crop pathogen sensors, hyperspectral crop sensors, impedance tomography, soil and aqueous nutrient sensing, graphene-based protein receptor sensors, terahertz technology, electrical inductance for root assessment or ripening, for example, phenotyping, protein conversion for livestock, harvesting selectivity, and then, for example, sensors that we can deploy in the field, like smart sensor pills for grain silos, to detect things like the temperature of a grain silo, if fermentation is occurring, if mold is starting to grow, and so on. So, in terms of then parameters that we monitor, this is a diagram quite useful, taken from a book published by Professor Goebel from Germany quite a long time ago now. But what it nicely does is actually looks at monitored parameters and divides it into kind of physical and chemical parameters. So when you start looking at sensors, you're looking at measurement techniques, which can be dependent on physical measurements or chemical measurements or a combination of both. An example of physical measurements would be, for example, measuring velocity, speed, distance. An example of chemical measurements would be, for example, measuring carbon monoxide, measuring pH. And so there are many basic sensors and different detection principles, which is summarized here. We have things like conductance, different kinds of electrolytes. But then you need to bring in understanding of the physics and the chemistry. So you combine quantum mechanics, you combine statistics, you combine thermodynamics, kinetics, and so on. And then, but to make all this happen, you need the materials, the technology. So things like development of ceramics, thick film technologies, thin film technologies, methods of depositing films like spin coating. All of these are important. And then you have many applications associated with sensors. So you have things like environmental control, medical diagnostic or screening applications. We have agricultural applications, as I spoke before. And so what you can see is that in sensor development, you combine many disciplines altogether, going from mathematics, physics, chemistry, and more or less every discipline you could think of comes together in the area of sensors. So what I'd like to do is very briefly talk about some gas sensors, biosensors, materials, some printing techniques, and a couple of example projects, and then want to very briefly to aspects of software and pattern recognition that are very important in processing information from sensors. So when we look at sensors for gas sensing, what you want to do is to be able to transduce a signal when a gas molecule absorbs onto the surface. And there are many materials that are developing. So some of them are inorganic, some of them are organic. So for example, for inorganic materials, you have things like semiconductor metal oxides, tin oxide, tungsten oxide, indium oxide, titanium oxide. And there's a lot of work going on around the world in this area in terms of developing materials. And depending also producing composite materials based on metal oxides for gas sensing. In parallel to this, there's been a revolution in organic semiconductors over the last 30 years. And so organic materials, like conducting polymers, metalloporphyrins, metallocyanides, are very important molecules in terms of development of materials that can be used as the sensitive surfaces of transducers for gases. Apart from these, you also have the 2D materials. So these are really materials that are like a single atom on a 2D surface. And these are able to also to change in conductance when gases are absorbed onto the surface. So we can develop like graphene vapor sensors, which are sensitive to compounds like ammonia. So for example, this is a graphene sensor. It's responding to ammonia, to carbon monoxide, to water, to nitrogen dioxide. And you can see the different types of polarities of the reaction, depending on whether the electrons are taken from graphene or whether electrons are donated into graphene from the gases or vapors that are absorbed onto the surface of the sensor. And there's a lot of physics involved in studying the absorption of molecules onto the surface of 2D materials, and also then looking at the desorption process of molecules. So if you think of a molecule hitting a surface, it will bind with a certain energy. And then it will move away from a surface again. And that energy is really dependent on the affinity of binding of the molecules onto the surface. So there's a lot of work going on, for example, solution processing of 2D materials, because until now, in fact, working with these materials are very difficult. So you cannot see them, and you need to develop methods of actually depositing these materials. So there's a lot of work involved in developing like inks, which allow you to print 2D materials onto the surface. And these are now an exciting area of development, where you can now buy a number of different conducting inks with different properties that you could use to make chemical synthesis. So in the Organic Materials Innovation Center, to which I belong, we work with many different materials. Mainly organic polymers of different types, 3D scaffolds, flexible sensors, organic phenotype transistors, keyboard resistors, and so on. And there's a lot of work going on in characterizing surfaces using atomic force microscopy and different kinds of methods. So one of the key skills that we have is synthesis. So we have skilled chemists who are involved in making organic materials. And one important aspect is many of these new materials are semiconductors. So they are polymers, they're plastic, but they conduct electricity. And so they have like a band gap which goes between non-conducting state and conducting state. And that transition can be both electronic, but it can also reflect in a change in color, because it's promoting electronics in different states. So in fact, your mobile telephone screens these days, many of these are made of conducting polymers, where you can dope them and de-dope them, and they change color. And you can do that magically. So apart from carbonization, we have formulation. So we can make inks, printable materials to print the materials. And then we fabricate samples. So we can print sensors, we can spin codes, we can do other methods of deposition, and so on. We have many application areas, such as printable electronics, photovoltaic devices, and one important area is really low-cost Internet of Things driven low-cost sensor systems. So printed electronics is another very, very important thing. So we can produce things like organic transistors based on new materials, polymers, oligomers. We can make sensors, and not just one type of sensor, but arrays of sensors based on these materials. We can make solar cells, photovoltaic devices based on organic materials. And these allow like a large scale, real-to-real printing of large, many meters of surface area of panel that we use as a photovoltaic. So, and as you can see, we have a lot of interdisciplinary effort across different schools in the University of Manchester. So we have a lot of funding came from different sources. And one of the important sources of funding is the Engineering and Science and Engineering and Physical Science Research Council in the which is part of the UK government funding. And so what they did was to put quite a lot of money into catapulting developing principles in purpose. So I was lucky enough to be involved in this innovative process. We started back in 2013. And so the form was called a Center for Innovative Manufacturing in large area electronics. And it involved a collaboration between 4 universities, one University of Cambridge, Imperial College, University of Manchester, and University of Wales, and plus companies that are involved in manufacturing. And the whole day was actually to develop innovative approaches to large area electronics and reduce the cost of integrating electronics and developing novel approaches for high throughput functional testing. Now, one of the problems that we have with traditional semiconductors is that you need to work in a clean room to make a semiconductor like silicon. If you use organic semiconductors, you can relax the requirements for working in a clean room. And you can also apply techniques like printing, visual printing. You can apply 3D printing techniques. You can apply stuff with different kinds of printing methods, which allow you to produce multifunctional materials onto different kinds of substrates, which can be rigid or flexible, depending on the application that you need. So this is one example that we produced a while ago. So this is actually a conducting polymer gas sensor array. And this has 4,006 individual sensor elements in one chip. So if the size of this chip is about 2 centimeters by 2 centimeters, it contains 4,006 sensors, and this is an expanded view of these elements. So each of these strips that you see here are conducting polymers, and each of those conducting polymers are different from each other. And so we can produce actually a lot of information from such a chip. So when we look at when we now look at the response to a gas, for example, this is a response to ammonia gas. Each pixel now that you see on that chip is responding, and the different colors you see actually are changing conductance associated with the polymer in each element. So what you can see is this pattern of information, and this is unique to different gases. So this can be a very sophisticated electronic nodes, where we have if you connect this out to a data processing system, a neural network, for example, then it's possible to identify and characterize really thousands of different types of gases. Another area that is really very important are printer sensors. So we have been involved with developing printing techniques for printing sensors, and not just the sensors, printing also the connectors to the sensors. So here we have a sensor where we have a heater, which is printed. We have this is a sensing layer, right? So we have electrodes which connect a sensing layer, and then we have another layer which is actually a bio recognition element, In this case, it's a polymer, polyamide. So we developed devices like these in order to detect ammonia. So this is one device where if you operate at room temperature, this is the kind of response you see at room temperature to ammonia, with different pulses of ammonia. If you have a heater underneath the sensor, you increase the absorption kinetics. So here you can see in the red, much faster kinetics of absorption and desorption when we run that sensor at 80 degrees. But these are kind of tricks you do with just with inkjet printing. Another area that we've been working on quite a lot is organic field effect transistors, where you have 3 electrodes, a source, a drain, and a gate electrode, and an organic semiconductor in between. And we can make arrays of these transistors containing different materials, and we can produce an array of sensors which have different selectivities and sensitivities to different gases. And again, just like the previous array of sensors that I showed you, we can produce an array of sensors which have the kind of built-in application as part of the sensor. And you can then produce electronic modes, which is very compact. So, in terms of the components of organic field effect transistor sensor array, we have different organic semiconductors. We have a substrate, which can be glass, silicon, plastic, PET, and so on. It can be polyamide. So there are many materials that you can actually use as a substrate. We have printers, which allow us to print the different layers of the electrode array. To make it work, you have to have the electronics. And associated with electronics is always the software. So all of these have to be combined together in order to produce functional devices. So we produce, for example, libraries of different kinds of polymers in solution. We have different kinds of low-loss substrates. So depending on the application, we have substrates that are biodegradable, disposable. We can actually print on paper, depending on the application. We use inkjet printing or different kinds of printing, and you can use simple electronics. And actually, a lot of software is open source. You can actually get a lot of source code from the internet, which can help you with geometrics in terms of analysis of the data coming from arrays of sensors. So this is a little bit more detail on some of the structures that we create. So, for example, this is a transistor where we're looking at the ceramic or silicon substrate, or the ceramic. We have an aluminium layer, a polymer layer, and then we sputter some gold on top to make electrical contact. And we can then characterize these kinds of electrodes. We can produce different kinds of simple electronics that can integrate these transistors. And you can produce a very simple piece of equipment in the laboratory that then allows you to discriminate between different kinds of gases, and you can look at different kinds of transistor performances as well. So when we look at organic field effect transistor, we're looking at devices which have 3 electrodes. A source, a drain, and a gate. So for people who have no experience with semiconductors, if you think of it of electrical resistance, an Ohm's law. If you provide a voltage between two electrodes of a resistor, you get a current which is proportional to the voltage and the and resistance. So if we have a switch, which is called a gate, we can switch that resistor on or off. Then we have a means of producing a device which inherently can operate between a threshold voltage where the device is off, and if you increase the voltage of the gate, you can change the point at which it switches on. So, if you look at the graph on the right hand side of the screen, what you see is a curve which reflects the voltage at which such devices can be switched on or off. So down here is non-conducting. If you increase the gate voltage, then the device starts to conduct. And depending on the voltage that you have between the drain and the source, you can have different curves of current voltage performance. And so by playing with these parameters, you can create different kinds of transistor devices, which can be used for many, many different purposes. So apart from sensing, you can use them for application, you can use them as logic circuits, use them in many, many ways. So this is an example of a device which can respond to NO2. And by using a semiconductor and doping the semiconductor appropriately, for example, with these molecules like this, we can produce devices which have different selectivity and sensitivities to gas. So this graph on the left shows a concentration response curve, where we're looking at change in resistance in ohms in response to the concentration of the gas. Similarly, we can look at different kinds of solvents, and we can look at the effect of the solvent that is being used to dissolve the polymers, and we can produce different devices which have different characteristics and different dielectrics depending on the solvent that is actually used in manufacturing. We can use these devices, single devices, or in arrays of cells. And we have methods of calculating the optimal number of devices in an array, which will be useful for discriminating or detecting particular types of gases. So in this case, for example, we're looking at the effect of 4 devices in detecting methanol, propanol, dimethyl phosphate, and acetone. And you can see these different patterns appearing, which we can actually now use the Q metrics to discriminate between different types of weights. We have also different types of geometric approaches, which allows us to select materials for different applications. So, for example, we can use geometrics to do what's called structure-activity relationship, where we can predict which material we need to use to detect a certain substance. And these are quite important things. So we use different kinds of neural networks, and we can plug in the structure of an analyte, plug in the structure of an organic conducting polymer, and we can predict which is the best material for use. One nice thing about using organic conducting polymers is that you can actually make them soluble. And if you can make a polymer soluble, that means you can use methods like split coating, inkjet printing, all kinds of deposition methods. So we've been using polymers, like this was called PGPPTT, which is a mixture of pyrrole and thiopene in this kind of structure. It's got very interesting characteristics. It's very stable ambient air, and it can produce very nice response curves in terms of the current voltage relationships when you make a semiconductor using this material. There are other materials like PETC, and what you can see here, they're all conjugated organic materials which conduct electricity. So there are now a number of different materials that are available that you can solidify, and it allows you to make devices. So we can produce these organic feedback transistor arrays where we can tailor the application and the number of devices produce instruments. So quite apart from semiconductors, you can also use other materials for chemical sensing. So for example, you can take a transistor, put an organic semiconductor on it, but also incorporate things like peptides, proteins, and biological materials. And you can then produce different kinds of recognition elements depending on what you incorporate. So these are devices that work in the air, detecting gases. But there are also configurations where you can work in an aqueous environment. So if you think of detecting a chemical in water, what you can do is use the same configuration of transistor where you have a source and a drain, but instead of having a gate electrode incorporated within the device, you can have a drop of water or the electrolyte, and you have an electrode which then is inserted into a drop of water that is sitting on the surface. Now, that blend of water, semiconductor, and this transistor configuration produces what we call EGOFET, an electrolyte gated organic field effect transistor. And this allows sensing of chemicals that are in water. So again, you see a change in conductance right between the source and drain electrode, which is dependent now on the binding of an analyte with the aqueous solution. You can use these things for detecting explosives. So, for example, this is a device that can detect nitrogen. And what you'll see on the graph is detection of 1 ppm of nitrogen. And you can produce concentration response curves, which can go from parts per billion levels to parts per million levels in terms of detection. And you can use different materials and produce different devices, and you can measure changing current and produce all kinds of devices that work. So as part of this innovative manufacturing proposal that we're involved in, we've been putting together arrays of electrodes that you can see here. And these arrays of electrodes are printed on plastic, on flexible surfaces, and they can be used as disposable electrodes. They can be used in many applications. We inkjet print the polymers out of each of these transistors, and we can produce devices that look a bit like this, but see on the right-hand side, and we can put electronics around them in order to make that instrumentation. So quite apart from those devices, in my laboratory, we work with many other types of transducers. So we have the Q-resistive gas sensors that we see on the left-hand side. We have these tech transistors that I just mentioned. We have electrochemical gas sensors, which is based on a catalytic activity between a gas and electrolyte within a system that behaves like a battery. We have Pellis devices, which are based on usually oxides that have some kind of catalytic activity like platinum. We have mass devices like warp crystal microbalances. We have surface fluid sensors. We have optical sensors like surface plasma resonance sensors. And so all of these are kind of platforms that we can use for chemical sensing. An important aspect in my research has been electronic nodes. And this comes broadly from how our own nodes actually works in practice. So if you think of when you snip, you are taking molecules into your nose, you're sampling molecules, and those molecules actually absorb onto receptors that are present inside the nose. And what we found a long time ago was actually those receptors, those sensors, are not very selective. So when one sensor responds to a particle paper, another sensor will also respond. But that other sensor may respond with a different selectivity and with a different sensitivity from the other one. So what we have is actually in our noses, not very selective sensors, but we have an array of sensors that have broad and overlapping specificities. And what the brain interprets as a smell is actually a pattern of information coming from this array. So in the array of sensors that I showed you previously, what we're trying to do is actually to mimic some of these aspects of biology. So when we look at an engineering diagram of the nodes, these are the sensors in the periphery of the nodes that respond to the vapors. They produce a signal, so they're the transducers. What we have then is interconnection between those sensors with an area which in biology is called the olfactory model, where we have convergence of sensory information, integration of information, and then producing features, extraction of features that are important in discriminating between one odor and another one. And when we think of what we're doing with the brain, is if I give you a cup of coffee to smell, you say, okay, I can smell something, I can detect it. Then you say, a little bit later, yes, it's coffee, or I don't recognize it. Okay? And then a little bit later, you say, oh, I like that smell, or I don't like it. And then a little bit later, you react to it. You say, okay, I will drink this cup of coffee. Or maybe I don't like it, I'll put it out again. So in many ways, the nose and the brain are processing information at different levels. So some of these things that we can actually mimic using gas sensor arrays with appropriate signal processing. So here we have a sensor array. We have signal processing systems, feature extraction to extract the patterns of information. And then we have methods of training neural networks, validating neural networks, and then methods of classifying what is learned. So if we teach a system like a baby, that this is an orange, this is lemon, this is pineapple, this is coffee, then once it is trained, we can give it an unknown order. And it will come back and say, okay, if I recognize it, or I don't recognize it. What is happening in the last few years is really development of what we call bioelectronics. So apart from the semiconductors that I spoke about, we have now with the increase in capacity of molecular biology and our understanding of biology and how the nose works, we can extract cells, we can extract proteins, we can extract receptors, we can extract different kinds of organ binding proteins from the primary systems of mammals, insects, and all of these have different capabilities of detecting particle chemicals selectively or not. And by combining these proteins onto single transducers, we can create sensors. So what we can do is take the human nose, for example, look at these cells, that these are receptor cells in the human nose. We have to take these out and throw them in culture. We can immobilize the cells onto an electrode array. And we can measure the electrical potentials that they produce when they actually react to an odor. So we have whole cell biosensors that are possible. We can extract the proteins from these receptors. So we can take, instead of having a cell, we can take just a protein that is involved in binding the chemical. And we can immobilize those onto a surface like graphene or onto an EcoPet, a water-gated transistor. And we can then produce transducer devices that are capable of detecting odors either in vapor phase or dissolved in the liquid medium. Similarly, so if you take our feedback transistor that I spoke about, the source of trade electrode, we can immobilize proteins between and produce transducers that are very interesting in terms of detection different kinds of smells. Another class of protein is what we call odor-binding proteins. So one difference between receptors that are found on the olfactory receptor cells is that receptors are normally membrane-bound proteins through the lipid environment. Odor-binding proteins are actually in the mucus over the receptor sheet. And they are soluble proteins, and they function in the process of partitioning hydrogen molecules from vapor into the aqueous environment before they can be sensed. And you can use these proteins also as receptors of biorecognition elements. So we can produce different kind of sensors in this way. So there are many different methods of immobilization of proteins. And I've been working with a group in France where they have the capacity of producing diamonds. They make synthetic diamonds. Well, diamond is actually a very interesting material. It's made of carbon. And what you can do is it's also biocompatible. So you can make diamond electrodes, which can be used, for example, in plants, in humans, in animals. And you can also make diamonds where you can immobilize proteins. So we have been working with this group to produce diamonds And what we have is like a surface which is covered with microcrystals of diamonds. And on the diamond, we can then immobilize proteins. So we can pattern the diamonds to make microelectrodes. So we can have like little microelectrodes, like 50 microns in diameter, and we use micromachining and so on to increase the capabilities of these devices. And we can graft different types of materials of diamond. So you can put diamond under many different sources. So you can make gravimetric mass transducers like force crystal microbalances, certain acoustic devices, cantilevers, and so on. All of these go to the diamond, and where you can then attach a protein onto or other materials onto diamond. So there are many different ways of doing this. But one thing that we've done is looked at photolytic proteins. Another class of protein called the major urine proteins. These are proteins found in mouse urine, and which can bind different odors and olfactory receptors themselves. So nylon is actually a very powerful substrate. It can be used in a way that no other is capable of. It's a semiconductor, and it's very clean. It has no oxide layer on it because it's very little. And because it's carbon, you could use carbon chemistry to functionalize it. We could actually put functional groups onto it. And these functional groups you can then use to attach different things like proteins, peptides, aptamers, or. So one thing that we've done is take a micro cantilever. So this is a cantilever. A cantilever is a device that vibrates like this. So it responds to mass. So if something hits the surface, it will bend. And we can measure that bending. And we can put diamond onto it, we can put proteins onto it, and we can measure the response of that cantilever to vapors. So what we see here is the response of this cantilever, put it in an olfactory center,
Itu kan
the vapor of acetyl.
mana?
And
Ui,
what we have here is different responses depending on the concentration. We can put different kinds of olfactory receptors onto this cantilever, and you get different selectivities of different compounds. So the printed gas sensor market is very important. And it's expected to reach like $7.6 billion worldwide in 2027. And so in Manchester, we've been working on biosensors, capacitor sensors, piezoelectric sensors, optical sensors, temperature sensors, humidity sensors, and so on. And of course, gas sensors. All of these using printed techniques. So the particular applications, depending on what you want to do. So with print sensors, you can make very large area sensors. You can make sensors that can be worn as part of clothing. So you can print them on metal, plastics, and so on, so they're conformal. You can have sensors that you're wearing, and you can't perceive them. So these are some sensors that we make. So this is a sensor for analyzing split. And it just disposable stripped electrodes, very simple electrodes. But I create things like printed disposable glucose sensors. You can make printed gas sensors, temperature sensors, mood detectors, and so on. And environmental monitoring sensors. So one thing that is very important is that printed gas sensors will play a very key role in Internet of Things development. So we have we've been going from the kind of traditional semiconductor type sensors to these printed devices, and then making devices that can respond to gases of different types. The one thing that you can think of with a printed gas sensor is that you can actually take a room like this and actually distribute sensors in the room. So then you can measure humidity, you can measure gases, pollution, fertility, buildings. You can think of putting sensors in the whole house with very cheap sensor technology. You can detect things like pollutants, NO2, VOCs, sulfur dioxide, ammonia, carbon monoxide. All of these are possible in terms of either home environments or industrial environments. And printable sensors are being used in things like precision agriculture, smart packaging, health, industry, smartphones, pollution, with many different successes. And the main advantage is they're very easy to fabricate. You don't need clean room facilities. They're low cost. You can produce very flexible sensors. And not only that, they can be very sustainable because you don't need to use metals, you don't need to use toxic materials. However, there are lots of challenges. And one of the problems of any kind of material is that very often printed sensors have low stability. So there's a lot of challenges in terms of producing sensitive, selective, stable sensors. And then the other challenge, important, is really sustainability, eco-friendliness, the speed of response, flexibility, the dynamic range, they can work over, and then when you scale that up very much. So there's a lot of work going on in terms of the challenges associated with sensors. So I've been talking quite a while now. So I don't know if anybody's got any questions on what I've been talking about.
Okay.
Yeah.
Thank you very much. I would like to ask you two questions. So the first one is I'm kind of lost in the diamond-based sensor, right? As far as I know, diamond is an isolator, right? Isolator. So the diamond take the role as not as conducting materials, right? For this system. So you can little bit recall about the diamond basics.
Okay. So yeah. So the question is to say diamond is non-conducting. However, if you want to make like a geometric electrode, you can open it before. Yeah. So if you open up the diamond before, then it becomes a conducting material. And if you want to make, for example, electrodes that can be implantable electrodes, then those boron lobes and diamond electrodes are very common. for example, for brain stimulation, brain management techniques, very often they will use diamond tip electrodes now. The type of diamond field that I showed you, now we're not conducting fields. So these were intended to be used as part of mass transducer. And what you do is you quote a transducer like a quartz crystal microbalance or surface acoustic wave device or cantilever with nanocrystals of diamond. You then put it in the plasma, and so you activate the surface, and then you can chemically modify the surface at that point to attach ligands, which can be used as reactive ligands, which is attached to a protein or peptides or aptamers or whatever you want to attach. And if you do that, then you can produce very, very powerful transducer, very stable. One advantage of using diamond is part of mass transducers, of course, like more crystal microbalances and surface acoustic wave devices. It's got a very high Q factor. So when you look at the frequency of resonance of the device, it becomes very, very sharp. And then, so that means you have very high sensitivity.
Oh, that's very clear explanation. Yeah, very clear. Just one other question.
Yeah.
Okay, for the last decade, I'm working with polyamide. You know, not small polymers like polyamide.
Yeah, polyamide, yes.
Yeah. Okay. But I mostly use polyamide for photovoltaic devices.
Yeah.
But I heard also they can use as a sensor, right? As a humidity sensor, ammonia sensor. Okay.
Yes.
I would like to ask you your perspective and challenges towards polyamide for sensor, because in the last maybe 2 years, the number of publications about polyamide as a sensor is reducing. So maybe what was this problem?
Okay. So polyethylene is a very, very powerful and interesting semiconductor. It exists in 3 oxidation forms. And so you can actually move from a non-conducting state to a conducting, highly conducting state very easily. And not only that, it changes color with each conducting state. So it can be used both optically as well as electrically in terms of sensors. For gas sensors, it has a very high affinity for ammonia. So a lot of applications use polyethylene as part of an ammonia-based sensor. And the reason for that is the lone pair of electrons on ammonia interacts very, very nicely with the nitrogen in the polyethylene. So you get very high affinity. Now, this is an advantage as well as a disadvantage, because you got very high affinity of binding, which means it's very slow to dissolve from the polyethylene surface. So if you use polyethylene just by itself, the sensor actually will not be very functional, because it will respond nicely, but then it will take hours to recover. So more recently, people have been using polyethylene as mixtures with metal oxides. So you can mix, for example, nanoparticles of an oxide like tin oxide or other metal oxides, which reduce the affinity of binding. So you get faster absorption dissolving. The other thing as well that you can do is to heat the sensor. So you put a small heat underneath and heat it up to about 80 degrees, and then you get a sensor that will respond quite nicely to changes in gas concentration. So, but apart from that, there are also many other application of what we are doing a semiconductor.
Okay. One question from my most that. Did you have experience in inspecting of aromatic compounds like the everything?
No, we repeat what you just said so that they can.
Okay. In Indonesia,
Yeah, so
ini pertanyaan saya dan saya ini ingin menanyakan apakah Pak Krishna punya pengalaman dalam mendeteksi aromatik kompon, ya, aromatik kompon seperti terpen. And if you have experience in detecting aromatic kompon like terpen.
yes, so the type of sensor technology that we use for gas sensor depends on the application. So with metal oxide based semiconductors, they are able to detect things like hydrocarbons. They can detect aromatic compounds with very high sensitivity. So metal oxide semiconductors normally are heated. So if you heat a metal oxide, like tin oxide or tungsten oxide, about 300 degrees, they turn into semiconductors. You have like a thin layer of oxygen on the surface that's absorbed. And molecules like benzene, aromatic compounds, they will displace oxygen on the surface. And you can see a very big change in conductance. Now, organic conducting polymers, they are more polar. So they have a big electric field over their surface. So they are not very sensitive to aromatic compounds. So if you wish to detect the surface, I prefer to use
Any other question? Please raise your hand. Silakan angkat tangan. Bertanya dalam bahasa Indonesia, that's okay.
Oh,
So I have a few more things I'd like to share with you. So one important aspect is in terms of the future development of sensors are sensors that are more efficient in terms of energy consumption. So everybody wants low power sensors. And so as I mentioned just now, things like metal oxide sensors need to be heated to high temperatures in order to make them work. And so there's a move right now in terms of developing sensor materials that actually are either self-heating, they can work at room temperature, or they're based on different techniques, like micromachining, which can allow these materials actually to function in different modes. So there's a lot of work, a lot of research going on in terms of developing sensors that are more energy efficient. So if you think now of making it like a flexible sensor, what I showed earlier was we could print a flexible heater onto plastic substrate. We can make a sensitive device by just putting a thin coating of a layer of oxide or polymer on top of that. And this then allows us to produce a device that consumes much less power than many commercial gas sensors. So this diagram shows you really the progression. So one is we can use many different materials. You have metal oxides, we have metal organic frameworks, you have conducting polymers, you have two-dimensional materials, you have things like carbon nanotubes, we have biological materials like proteins. All of these can be used as the front end for detecting gases or odors. So, in order to make them manufacturable, you need some way of formulating something that's printable. So typically, we need some magic here, some chemistry to make these solids. And there's a lot of research going on in this area. So from these, we can produce things like optical sensors, we can produce printed electrodes, hot plates, and so on. We can produce large sensor arrays. We can produce devices like the feedback transistors that I showed you. We can, and then we can measure responses. So these can be either chemoresistive, and that you measure a change in either voltage or current. Or if you use feedback transistors, typically you provide a gate voltage and measure change in current between the source and drain electrodes. So there are a number of applications, as I mentioned. So in environment, we have things like air quality, environmental pollution. We have in health, because there are many biomedical devices and pharmaceutical devices that can benefit from gases. So, for example, I'm working with a group which is involved in analyzing urine from cancer patients. And we can look at the volatiles in urine and decide whether or not this person is clear of cancer or not. Security is very important. Things like detecting drugs, detecting explosives, food quality, and looking at the quality of the food, the shelf life of food, rancidity. All of these important aspects of food. Farming actually produces a lot of pollution. And so you have a lot of food emissions for farming. So if you have chicken farms and you have animal husbandry, you could produce a lot of both of them. And then in manufacturing, chemical industry produces a lot of vapors. And all of these can benefit from sensors in the environment. And by producing large scale, easily manufacturable, low cost electrodes, we can change the scene in terms of gases. So one project that integrates a lot of things together was a project that we had as part of this innovative manufacturing project. So as part of a group which involved Manchester and University of Cambridge, we produced a sensor array based on organic feedback transistors. We printed using more inkjet printing techniques and front end. And these are transistors and logic circuits based on organic semiconductors that just print on the flexible substrate. We printed a multiplexer circuit on it. So then we have a whole front end, which is just based on a flexible substrate containing printed electrons. We then connected that to a conventional silicon microcontroller, a solar cell for energy, and then a display. And this produces a very cheap device. So, and what we ended up with was really several things. Key resistance, a change in resistance. The organic feedback transistors there is a vegetative current, vegetative threshold voltage, and so on. And this array of sensors, which allows us to produce something that gives an electrical response. So just to give you a quick idea of what is involved in the manufacture of these devices. So I'll just present this and then I will stop. So in terms of fabrication of organic field effect transistors, one important thing is the materials that are used. So what you want is to produce a material that has steel in ambient environments. When you think of our environment, it's humid, very humid. It changes the temperature, and but you want a very cheap device to be stable in your environment. So what we produce are polymers, which have things like fluorine in them. So these are polymers that are like high dielectric materials, and we use this as insulators on the gate electrode. So what we do is take like a plastic substrate, which can be used any material. We deposit a gate electrode by evaporating metal. We spin coat a dielectric on top of that gate electrode. So this is now an insulating material. We cap that. So the problem now is when you spin a very hydrophobic material onto a substrate, it doesn't allow easily spreading of all the materials. So if you put a drop of water on it, it forms like a meniscus. So what you put is what's called a capping layer, which allows materials to spread when it's placed in top. So we then put on the source of gradient electrodes. So you evaporate metal on top of that. We then coat that with the organic semiconductor. So now we have a sensor. And so we have this layer, the plastic substrate, the gate, a dielectric, a capping layer, and the conducting polymer. And we can produce these arrays of electrodes that look like this. So what you can see is that using very simple manufacturing techniques, without a clean room, we can produce very functional devices. So the kind of plastic devices that we produce now will look like this. So what you see here are two sensor arrays inserted into this socket. These are commercial electronics for data acquisition. This is a small pump that passes air or vapor across the sensors. And this little device here can be used for many applications. So I will stop here. Any questions? Yes, Mark.
Krishna, could you little bit explain what the graph when it function in the sensor development? Because in this department we start to do with this kind of material for potentiometric sensor.
And so the graphene.
Graphene, yeah.
Right. Okay, so graphene is a two-dimensional material, and in terms of manufacture, typically you get graphene flakes and so and which are soluble in a solution. Now, graphene by itself is not good as a sensing material. Graphene oxide, like oxidized graphene oxide, you have an O, which is O minus on surface. Actually, is much more easy material to work with in terms of sensing. So, graphene, you can immobilize it as between a source and drain electrode. So if you take the ink containing graphene, graphene oxide, you can spin coat it, you can inkjet print it between two conducting electrodes. And
Just the graphene oxide,
yeah,
without any mixture or something like that.
yeah, because you don't have to, and you end up now with something that is conducting. That it behaves like a transistor, which turns on a very low threshold. So when a gas molecule hits a surface, it absorbs. This causes doping or de-doping of graphene oxide. So you get what happens is that you get very electron. You get electron transfer due to absorption of molecules on the surface, and the donation or the taking of electrons from graphene causes a change in resistance. You can measure a change in current between the source and drain. So it actually is like a resistor or like a low threshold voltage transistor. Now, many people try using graphene oxide. Yeah, so many people have tried using graphene oxide and gas sensing. In comparison with other gas sensing materials, it is actually performed very poorly. The stability is not good compared to other gas sensing materials. Because very often contaminants absorb onto the surface of graphene and will not come off. So the cells have poor purity, high voltage, and reversibility quite depends on what the further cells. So I would not really advise using graphene as a sensitive material. However, what's now coming available is actually functionalizing graphene. So apart from graphene oxide, you can attach molecules onto graphene. So they're now available functionalized inks, which are two-dimensional base, but they have functional groups like aromatic groups on the surface, and these are much more stable.
Thank you.
Thank you very much for Professor Krishna for your presentation. Nice presentation. We hope that all the information will be give us knowledge and inspire us to research. Thank you very much, and we would like to move to the hall.
Thank you very much, Dr. Gita, for guiding us through this insightful session. May the session bring us new insight and inspiration. And also, we would like to express our deepest gratitude to Professor Krishna for this informative presentation on sensor research and development. Also, we also extend our thanks to all participants for your engagement today. Okay, give big applause to all of us. We come to the end of today's event. On behalf of Department of Chemistry, Faculty of Mathematics and Natural Sciences, Universitas Jember, we hope today's session has been inspiring and educational for all of us. Thank you for joining us, and we look forward to seeing you in future events. This concludes our guest lecture, and I'm as the MC want to say sorry if there are some mistakes along this event. Again, I will wrap up this session and have a wonderful day.